Hello everyone. So let us continue our discussion on the types of pericyclic reaction. So next type, that is the cycloaddition reactions. Okay. So in the previous video we talked about the first type of the pericyclic reaction, and that was electrocyclic reaction. So in that we had only one reactant. So it was an intramolecular reaction. However, cycloaddition is a intermolecular reactions where we have two different compounds having pi bonds, okay, involved in the reaction, leading to the formation of a cyclic compound. So in the electrocyclic reaction we had the formation of the cyclic compound, as well as it was a reversible reaction, okay. And but that was intramolecular. Electrocyclic reaction was intramolecular, though it gave you a cyclic compound in the process. However, cycloaddition reaction is an intermolecular reactions where we have two different compounds with the pi bond. So that is the basic difference that you can see between the electrocyclic reaction and the cycloaddition reaction. So in the cycloaddition reaction comes your important reaction that you have studied, and that is your Diels-Alder reaction. So Diels-Alder reaction. Okay, so Diels-Alder reaction, if you might have gone into a little bit of detail, it is a 4+2 cycloaddition. It is a 4+2 cycloaddition. Now what do you mean by a 4+2 cycloaddition? We have 4 pi electrons, okay, and then reacting with a 2 pi electron system. We have two reactants. One is having 4 pi electrons, and the second system has 2 pi electrons, okay. So when we have such a intermolecular reaction, it leads to the formation of a cyclic compound. So here again, reorganization of the pi electrons is what is happening here, and it is also forming via a cyclic transition state. Now I think you are pretty confident now how to draw it. So let me first draw the intact bonds with solid lines. So that I have drawn, okay. Now the inside bonds, okay, and then the cyclic compound, this bond, these two bonds are kind of new bonds, right? So that I'll show, and the other intact bond is this one. This particular bond is intact, okay. So now what is happening? You have the breakage of this pi bond happening here. We have the formation of a pi bond here, okay, in the product. So we show it, that one also with a dotted line, and then we have breakage of this pi bond happening, so that we again show with a dotted line, and then we have the formation of two new sigma bonds here, okay, that we will again show like this, okay. And then you have a pi bond here in the 2 pi system being broken, so that we will join out here. So this is the cyclic transition state for the Diels-Alder reaction. So this is the cyclic transition state, okay. So this particular transition state ultimately give you your cyclic product, in this case cyclohexene, okay. So in the product, what is all you can see? Two new sigma bonds are formed, okay, and the product has 2 pi bonds fewer than the total pi bonds in the reactant, okay. So if you talk about the reactants, how many pi bonds are there? There are 1, 2 and 3 pi bonds. Now in the product you have only 1 pi bond, so that means 2 pi bonds are less in the cyclic product, because those pi bonds have been used up in formation of the 2 new sigma bonds, okay. So this is so such type of reactions where you have two different reaction involving electron relocalization leading to the formation of a cyclic compound via a cyclic transition state. Such type of pericyclic reactions would be categorized under the class of cycloaddition reactions. Okay, let's move further. If we talk about the third type of pericyclic reaction, it is nothing but the sigmatropic rearrangement. Okay, so let's look at the definition first. It's an intramolecular rearrangement. So again, now we have come to intramolecular. We have a single reactant here. So an intramolecular rearrangement where a sigma bond is broken and a new one is formed along with the pi bond being rearranged. Okay, so an important difference that you note in among the sigmatropic reaction is here we have the breakage of the sigma bond happening and a new one is formed. So there is a sigma bond broken and a new sigma bond is formed, and the pi bond is just rearranged. You do not have lessening of the pi bond. If you remember the previous video when we talked about the electrocyclic reaction, there the pi bond were reduced by 1. In the cycloaddition reaction, it was reduced by 2. However, in sigmatropic rearrangement, you do not have any kind of pi bond being lost in the process, and whatever sigma bond is broken, it is also being formed. So that is why here instead of calling it a sigmatropic reaction, we are calling it as sigmatropic rearrangement, because basically here what is happening is only a rearrangement of the electronic system is only happening, and that is why such type of pericyclic reactions where you have electron reorganization and leading to the breakage of sigma bond and formation of a new one and rearrangement of the pi bonds in the process via a cyclic transition state will be classified under the class of sigmatropic rearrangement. Okay, so let's look at some of the reactions there. Two different types of reactions I have shown here. So this is one compound like this, and here you have a sigma bond here and you have two pi bonds here at the end. Okay, now we have electron reorganization happening. You have a sigma bond being broken here, and then this pi bond is getting converted to another new set of sigma bond. So in the process, what you see here is a sigma bond was broken in the reactant and it was formed back in the product, and these two pi bonds have shifted to their new positions here. So the number of bonds is conserved in the sigmatropic rearrangement. There is no loss of bond, no loss of sigma bond, no loss of pi bond. And here the sigma bond that is being broken is kind of middle of the two pi bond. This is one type of sigmatropic rearrangement where the sigma bond broken is kind of in the middle of the pi system. Okay, these are the pi system, these are the end pi system, and you have the sigma bond that is broken in the sigmatropic rearrangement is kind of in the middle of the two pi systems. Okay, now there is another sigmatropic rearrangement. What you see here is we have again two pi system and you have the hydrogen. Okay, so you have this sigma bond, that is CH sigma bond, is being broken in the process. So kind of movement of electrons happening in this fashion. So you got the rearranged pi electrons here, and the sigma bond is now formed with this particular carbon atom leading to CH3 here. Okay, so a sigma bond has been rearranged, broken in the reactant and formed in the product, and your pi bonds have been rearranged in the process. But here the sigma bond that is broken is not at the middle of the pi system, but rather it is at the end of the pi system. So we can expect two types of sigmatropic rearrangement. One type involving the sigma bond being broken at the middle, okay, and one in which the sigma bond that is broken will be at the end of the pi system. Okay, so this is these are the various types of pericyclic reactions. So please go through each of these examples, write it down, and try to practice their movement of electrons. Then you would be able to understand them pretty clearly. Let me draw one transition state for you, though I would like you to draw it yourself just to show how it is happening. So the bonds which are not involved in forming, I am just writing them as such. Okay, these bonds are not involved in breakage, and this CH3 is not involved in any breakage or forming. So those I have shown by solid line. Others I am going to show with a dotted line now. Now since you know I have discussed enough, so you know how to draw it now, a cyclic transition state. That is what I am drawing here. So this is the cyclic transition state for this particular reaction, which is leading to the formation of this particular product. So every pericyclic reaction involve an electron reorganization, and what you see is happening is the electron reorganization is happening via a cyclic transition state, which ultimately lead to the formation of the product. Now in all these reactions, you might have seen that what is happening is the pi bonds are the one that are actually involved in the formation of in these reactions. Pi bond reorganization is what is mostly happening in all these three pericyclic reactions. So while we are going to reason out how it affects the products that are formed in our pericyclic reactions, uh, when we use certain theories to explain the stereoselectivity in the pericyclic reactions, because pericyclic reactions are highly stereoselective, and some of the reactions happens under thermal condition and some of them happens at the photochemical condition. So why there is so much of specificity in the reactant configuration and the product thereby observed, and so much specificity in the condition that is used, all this can be reasoned out via use of pi molecular orbitals. So that we would be seeing in the coming lectures of the pericyclic reactions. So I hope you have understood the different types of pericyclic reactions. We are going to look into each of these pericyclic reaction and look into the details of them. Thank you all.